Folks, let's get started. So it's my pleasure to welcome you all and to welcome Professor Yulin Pan, who's our speaker in our winter CNRE winter seminar series. And Yulin is an assistant professor in the Department of Naval Architecture and Marine Engineering. He received his PhD from MIT, along with a minor in Navy in ocean engineering, along with a minor in math. And he's one of the leading experts in nonlinear wave dynamics and wave turbulence. His specialty, his research is primarily in theoretical and computational hydrodynamics with this focus on wave turbulence and nonlinear wave dynamics. And he's made contributions apart from those areas to tidal flows, propeller flows, and bio-inspired foil propulsion. And an interesting thing about him is that in addition to his scholarly interests, Yulin is also an active writer of the popular science of fluid mechanics. So he is, in that sense, he's a Renaissance man. So, Yulin, thank you again for giving this talk today. I look forward to hearing it.
Thank you, Maharaj, for the introduction. Can you all hear me if I talk like this? Okay. Thanks for coming. And I'm going to give a presentation on spectral diffusion in wave turbulence application to water waves and its generalization. So first of all, let me give you an overview of today's presentation. It's not working for some reason. Okay, all right. So I'll start by giving you an introduction to the wave turbulence theory. And in particular, I'm going to do this in the context of surface gravity waves, which is most relevant to today's talk. And then I'm going to introduce you the concept of spectral diffusion, also for surface gravity waves. And I will show you that this is a new theory developed specifically to interpret some inverse cascade spectra observed in experiments and simulations. Excuse me. And finally, we are going to show some generalization of the theory using the so-called MMT model. I will tell you what MMT is later. So this work involved myself and three collaborators, Alex Kravkevich, Sergei Natlenko, and Jalal Shatar. So basically, my research is on the theory and the computation of wave turbulence. So a great portion is on these topics. And this talk will be more on the theoretical side. So if you have any questions, please just stop me anytime you would like to. And I think that'll be easier for everyone. Okay. All right, so let me first tell you what is wave turbulence. So you guys know hydrodynamic turbulence very well. So the best way is probably to introduce this as an analogy to hydrodynamic turbulence. In hydrodynamic turbulence, we have a flow field like this, and we know that we have structures of different scales interacting with each other in this picture. And one way to understand that is to say that we have a vortex energy cascade in the sense that we have energy injected to the flow field to form the large vortices. And then through the interaction, the large vortices pass energy to smaller vortices. And finally, the energy gets dissipated at smaller vortices, even smaller vortices in the field. If we turn to a statistical description of this picture, because the dynamics is so complicated, then most statistical description come from the dimensional analysis for the hydrodynamic turbulence. For example, you all know the K41 theory, etc. So it is pretty difficult to develop statistical description from analytical theory for hydrodynamic turbulence. And this problem is referred to as the last unsolved problem for classical physics by Richard Feynman. So on the other hand, we have wave turbulence where we have a wave field where the long waves interact with the short waves. And the dynamical picture is somewhat similar. So we have a wave energy cascade in the sense that energy is injected to form the long waves, and long waves pass energy to short waves, and finally energy gets dissipated at the shortest wave in the field. So if we turn to the statistical description again, it turns out that for wave turbulence, we're able, or it's easier, somewhat easier to develop some analytical theory for the statistical description. And this talk, I will introduce you some key elements in the description, namely the wave kinetic equation and the Kolmogorov-Zakharov solution for the equation. So the reason that we have this problem is a bit easier for waves is because if you look at the dispersive PD that governs wave motion, this PD usually is associated with some small parameters. And this small parameter come from that the nonlinear term of the PD is much smaller than the linear dispersive term of PD. So we can make use of that small parameter to develop lots of theory from it. But this is not possible for hydrodynamic turbulence, because for hydrodynamic turbulence, the nonlinear term, namely the inertial term, is big when we have high Reynolds number flow. So this approach is not directly applicable to hydrodynamic turbulence. And for the latter, we need something else. But in this talk, let's focus on the wave turbulence. Okay, so now we have understood that wave turbulence basically gives us a statistical description of random wave field. There are many systems like this in nature, which is associated with a random wave field, all the way from quantum scale to cosmological scale. On the quantum side, one example is a Bose-Einstein condensate, where we have density waves of particles in this condensate. And these waves are well described by the so-called nonlinear Schrodinger equation. And there are lots of theory developed recently for the Bose-Einstein condensate in terms of wave turbulence. And it shows very good agreement with the theory and the simulations. So on the classical side, one example would be the ocean wave. So this not only includes the surface waves on the ocean surface, but also the waves in the interior of the ocean. For example, the so-called internal gravity waves and the Rossby waves. So many different types of waves in the ocean. And finally, for the cosmological problem, we have the gravitational wave that also has a wave turbulence description. And it seems that these descriptions can have important implications of our early universe. So for these very diversified systems, the goal of wave turbulence is actually pretty unified. In the leading order, we are interested in two things. The first thing is how did the spectrum evolve? And second thing is what is the stationary turbulent state of the system? So these are also common problems for the hydrodynamic turbulence. So next, I'm going to introduce the wave turbulence theory and to tell you how to obtain the solution to these two problems. And I'm going to do that in the context of surface gravity waves. So for that purpose, I'm going to first tell you what is the Gamni equation for surface gravity wave. So this is in potential flow. Okay, so basically this Gamni equation, we also call it the primitive dynamical equation, gives us information about the evolution of a free surface between air and water. So there are two variables involved in the dynamical equation. The first one is eta, that is surface elevation. So this is a function of x, y as a horizontal plane, so two-dimensional horizontal plane, and time t. And another variable is called psi. So this is also a function of x, y, and t. And this is essentially the surface velocity potential. The way we obtain this quantity is that we first define the velocity potential in potential flow that is valid in the whole field of the water. And then this phi is a function of x, y, z, and t. If we make z equal to eta, and then we get the surface velocity potential psi. So the Gamni equation is completely written in terms of eta and psi. So you see these two equations are the evolution for the surface elevation and the evolution for the surface potential. So if you solve this equation, yeah.
Sorry, you have psi of xyt equals phi of xy eta t. I don't.
Yeah.
What happened to I don't understand that equivalence.
Sure. Okay. So let me explain this a little bit more. So we start from the velocity potential phi.
Yeah.
So the velocity potential phi is a function of x, y, z, t. So it's a whole field.
Correct.
And we are interested in what happens on the surface.
Oh, eta is a
surface. Yeah, eta is z. Maybe I should put z to eta. Then.
No.
Yeah. So then it becomes a two-dimensional thing. Okay. So then we have these two evolution equations. If we are given an initial condition and we solve this, then we know the detailed evolution of the free surface. Okay, so one thing to be noted is that for these two equations, the right-hand side is pretty straightforward to evaluate, except the function of phi z at eta. So phi z at eta basically means the z derivative of the potential function at the free surface. In other words, this is the vertical velocity of the particle at the free surface. So this thing is not directly known from eta and psi. And to determine this, we need to solve a boundary value problem. The problem basically says that we know the potential value psi on the surface, and we know that the field satisfies the Laplace equation, and how do we get the interior value so that we can evaluate the derivative. So this is a boundary value problem. You can solve it numerically, and you can also do it analytically if the surface perturbation is small. So so essentially, this is something like a Poisson equation for NS problem, that you need to solve this at each time instant to give you the value to evaluate the right-hand side of the equation. Okay, now let's talk more about theory for now. So what we can do with this, if we start from this primitive dynamical equation, if we work on the wave turbulence theory. The first step of the theory is that we start from this equation and we derive something called wave kinetic equation. So this is under some conditions, which I wrote here. I will tell you more about that later. So if we look at this wave kinetic equation, it is written here. If you think about the original dynamical equation to describe the detailed dynamics of the free surface, then this wave kinetic equation actually tells you the evolution of the spectrum of the waves. Here, this n of k is called wave action spectrum. So it basically means n as a function of two-dimensional wave number k. Okay, so this thing is defined as an energy spectrum divided by the frequency of the wave. So you can think of this way: if you know nk, you know the energy spectrum, and then you know whatever happens to the energy spectrum. It's just multiplied by a function of omega. So if you look at the right-hand side of the equation, it involves two dot functions, in particular for k and for the frequency omega. So these two conditions are called resonance condition for quartet resonance, because we have four waves, so we have quartet resonance for now. So what it does on the right-hand side is basically we pick up the wave number k1, k2, and k3 associated with the frequency omega 1, omega 2, omega 3. We make them to have a resonance with wave number k. And we integrate over all these resonance. That gives us how the wave spectrum at k evolved in time. So this is the meaning of the equation. And you see that we also have an interaction coefficient t, which is a function of both k, k1, k2, and k3. So this thing basically tells us that for each interaction, how large is its strength? So what is its effect on the evolution of the at k? Yeah.
Can I ask a question? There's a K1, a K2, K3,
Yeah.
which I understand is wave numbers in three directions.
Yeah.
But then there's an omega 1, omega 2, omega 3.
Yeah.
As opposed to one omega since there's one, I'm having some.
Yeah, so maybe I should say a little bit more here. So if we only look at the linear part of this equation, it means we have linear wave. So linear wave, one thing for linear wave is that we can look at this dispersion relation. Dispersion relation basically means for each k, we can compute the omega. So that's why we say surface gravities are dispersive, because for different wavelengths, the frequency is different and the phase speed is different, so they become dispersive with time. So this omega for surface gravity, basically omega equal to k to the half. So given k, you can compute this omega. Okay. So that's how. I should add that piece.
Well, there's like four waves interaction. What's the reason of four-wave interaction?
Is there a reason for four-wave interaction? Okay, that's a good question. Some system has three-wave interaction, but for this system, if we look at three-wave, k1 plus k2 equal to k3, omega 1 plus omega 2 equal to omega 3, and we need to connect k and omega with this dispersion relation. There's no solution to that. So you cannot find any k, k1, k2, k3, satisfy that equation, both k and omega. You can never find, it's proved mathematically. So you have to go to four-wave. That's actually, okay, I will mention that shortly, actually. So there are lots of wave kinetic equations for different systems, but for this one, for surface gravity wave, this is first derived by Klaus Hasselmann, and he got the Nobel Prize a few years ago, and this is actually the most important work of his early career. So let me say a few more words on wave kinetic equation. I don't know if any of you do wave modeling. So if you do wave modeling, you probably know there's software called WaveWatch 3. So that's something employed by NOAA to do operational forecast for the global wave state in the ocean. So this equation is actually a central piece of the WaveWatch 3. It's employed in that software to compute the wave interactions in addition to other wind forcing dissipation terms. So this is a part of the centerpiece. But the interesting thing is that for people who do wave modeling actually do not understand this equation. But people who understand this equation actually do not do wave modeling. So that is what I observed in the past. So anyway, so I'll tell you a little bit more about the condition where we can go from the primitive equation to the wave primitive dynamical equation to the wave kinetic equation. So I will just say this very briefly because this is not the important thing for today's talk. But if you are interested, we can expand more. The first thing is that we want to assume a random wave field. So the phase is random. Sometimes we assume the amplitude is random, and then the statistic is regards to this random field. And the second thing is something called normal form transformation. This is related to the question of the three-wave thing, because if you look at the original equation, it has quadratic terms. Quadratic terms means three-wave interaction because you can there are only three quantities, right? But the problem is that, as I mentioned, there is no three-way interaction for the system. There's no solution to that, to the resonance condition. So we need to get rid of the quadratic term. So we do something called normal form transformation to get rid of the quadratic term, to transform the equation that only contains cubic terms. And the cubic term finally gives us the final wave kinetic equation that involves only quartet resonance or four-wave resonance. And and finally, we need something called kinetic limit. It means we need the nonlinearity of the system to be small. Here, the nonlinearity basically means the wave steepness, and that is related to the size of the nonlinear term in the equation. And we need the domain size out go to infinity, so we have infinite number of waves in the system. So with these conditions, we get wave kinetic equation, and then we can go to step 2 to find the solution, stationary solution to this equation. This basically means we want to find a parallel solution of nk. Basically means we want to find a parallel solution of nk so that the right-hand side of this equation goes to 0. Okay, so it turns out that we can do that under the condition of an isotropic spectrum. And there are two types of stationary solutions we can find. The first one is called Rayleigh-Jeans solution or Rayleigh-Jeans spectrum. So this is not very relevant to today's talk, so I'm not going to tell you too much about that. And the important thing are the turbulent solution, which is called Kolmogorov-Zakharov spectrum. And you can see that this is actually analogous to the Kolmogorov spectrum in hydrodynamic turbulence. So for this system, there are two solutions of KZ spectrum. The first one corresponds to the forward cascade of energy. So this is written as NK, which is a wave action spectrum equal to some constant Cp, known as Kolmogorov constant, times flux of energy P to the power of 1/3, and times wave number K to the -4. And there is also another solution corresponding to an inverse cascade of wave action that is written as another constant Cq times constant flux of action Q to the power of 1/3 times K to the -23/6. So this basically means if we imagine a situation that we put forcing at some particular wave number K here, then we expect to observe two things. At smaller scale, we expect to observe a K to the -4 spectrum. And this also sends constant flux of energy to small scales. And at larger scale, we expect to find a K to the -23/6 spectrum, which is the inverse cascade spectrum that carries constant amount of flux to large scales. So this type of solution is first obtained by Zakharov. And actually, he did this first for acoustic waves and then for surface gravity waves. So of these two solutions, I would like to put a note on the inverse cascade solution because this is actually very important in the historical development of turbulence theory, in the sense that this is one of the first inverse cascade spectrum found by someone, by some human. Actually, this is done at similar time when Krashen find the solution for the inverse cascade in 2D turbulence. So they did the work independently at similar time, and because of that, partly because of that, they got the Dirac Medal in 2003. And if you look at citation, the inverse cascade part probably is very important because it's set for exact results and the prediction of the inverse cascades. Of course, question for 2D turbulence and Zakharov for surface gravity waves. Okay. Now we have a outline of a beautiful theory that gives us the exact solution. Our next goal is to look at what observation tells us, and the observation includes experiments, simulations, and field measurements. So let's start from the forward cascade spectrum. And on this page, I show you some plots of results from simulations, experiments, and field measurements for the forward cascade. And the problem is that for each of these figures, the original figure is plotted with different vertical and horizontal axes. Sometimes they plot with action spectrum, sometimes with energy spectrum, sometimes versus with number k, sometimes versus frequency omega. So every plot is different. What I did is I convert everything to be nk. So, and I write that on top of the figure. So you only need to look at what I wrote there. So the first row gives you the result from two simulations of the primitive dynamical equation. And the only difference is that the first one is for the K turbulence condition, and second one is for the false dissipative turbulence condition. And for both cases, you see that there's a large long inertial range with a slope that agrees with the theory pretty well in K to the minus 4. And for experiments and the field measurements, it is the bottom row. So the first two figures are from experiments obtained done at different wave tanks. And you see that they both get a spectrum that's close to K to the minus 4. And the last one is it's a field measurement in the ocean. I think that they use radar probably. And also they get a spectrum of K to the minus 4 for some range. So if I'm gonna make some conclusion from this page, I would say that in general, the simulations and experiments agree with theory under proper conditions. So here I highlight under proper conditions because there are also experiments that produce a different spectrum, but those are usually considered to be conducted at some situation that not agree well with the theory. So in general, it is fine. Okay, so how about inverse cascade? So it's a completely different story. This is the recent paper published about 2 years ago, maybe 1 year ago, on a simulation of the primitive dynamical equation for the inverse cascade scenario. So we place the forcing, but they place the forcing at small scales, and the purpose is to observe what happens at large scales. So you see that there's a very good developed parallel range, and if you measure the slope, actually it's close to K to the minus 3. Precisely, it is minus 3.07. That is that is very different from the KT solution of 23/6. So this number is close to 4, and it's denoted by the dashed line here. So there's a clear difference in the results. And if you look at the experiments, the first two figures shows you some experiments done at the same wave tank, but the faulting conditions are a little bit different. So they obtain K to the minus 3 and K to the minus 2.5, which is somewhat closer to the K to the minus 3 solution instead of the KT solution. And the last experiment is from a different wave tank. And you see that we have two spectrum plotted here, one at low nonlinear level and the other at high nonlinearity level. So here by nonlinearity level, I basically mean the energy level of the system. For higher energy level, we have a higher spectrum. For lower energy level, we have a lower spectrum. So if you look at the slope, then this one, the lower one gives us K to the minus 3, and the higher one gives us K to the minus 3.65. So if you look closer, you will find that the K to the minus 3 spectrum is associated with a larger peak at smaller, at large scales. So this basically means that in this experiments, we have a strong long wave background together with a power law solution. And for the higher spectrum, this peak is there, but it's not as obvious as a lower energy one. So this peak is actually also pretty obvious in the numerical simulation, that we have a very strong long wave background associated with this power law of k to the minus 3. So if I make a conclusion, we would say that the simulation and the experiment suggest the k to the minus 3 instead of the KZ solution, especially in the case where we see a strong long wave background together with the spectrum. So this strong long wave background, we'll call it a condensate. So this basically means a strong long wave background. It's something that formed very naturally. The reason is that because we have an inverse cascade, we keep pumping energy to large scales. But we have, on the other hand, we have a finite size box, either a tank or a simulation domain. So the energy cannot go anywhere, but gets accumulated at large scale to form this large structure. So on the other, so this picture basically shows you some structure of the condensate obtained from the simulations in the previous page. And they are ring-shaped structure. They do not reach k to 0 or even k to 1, which is the fundamental mode of the tank. The reason is because when this is pushed to the large scales, the wave number becomes very discrete at large scale. There are only very finite number of wave number you can do when k is close to 0, and this prohibits energy transfer. This is called finite size effect in wave turbulence. But anyway, it does not go to the k equal to 0 or one mode. It exhibits a ring-like structure in the k space. So our next goal is to understand why this affects the power law of solution. And essentially, we want to establish a theory that accounts for the structure and give us the right prediction from the simulation experiments. Yeah.
In the case of an experiment, the energy goes to longer wave numbers, still it's constrained by the tank or the.
Yeah.
What happens in the ocean where you don't have that
ocean, right? In the ocean, usually it's not. If you think about surface waves, usually it's not. But there are other cases like internal gravity waves. You have a very long wave that is on the depth of the ocean.
Yeah.
Ocean that
There is a
might
length
happen.
scale imposed.
Yeah.
But in the ocean, it goes to larger and larger and the energy keeps decreasing, or something has to cap it, right? Because it can't go to the same energy can't go to
So
infinite.
for surface gravity, it
Maybe.
goes larger and larger. Yes, well, I don't know if it goes to very long, what happens.
Right, something
Yeah,
has to.
something has to happen. Yeah, I don't know the answer to that question. But yes, this mainly happens in simulations and experiments.
I
But
see.
in the ocean, there could be other situations. For example, you could have maybe this could not result from the inverse cascade, but you probably have a direct forcing a large scale from wind or something to give a large structure, and then you have this spectrum at smaller scale. That is possible.
I see.
Yeah, it's just not from inverse cascade.
I see. Thank you.
Yeah. Yes.
With the shape of the container?
It's either rectangular or a box, or yeah, square.
Would the shape have an effect on this condensate?
It might have some effect, but I would expect not too much. So this is like the container is not isotropic. It's a box, right? But this is almost isotropic eventually. So I would expect there would be some influence, but not strong. Yeah, that's what I thought. Okay. Any more questions? Okay, so our goal is to establish such a theory, and the theory is in this paper published last year. So basically, there are two approaches to do that. For the first approach, we start from the wave kinetic equation. Now you all know what it is. So we start from with kinetic equation, we are going to assume the dominance of non-local interactions. So what I mean by this is that if we look at the spectrum, now we have a very strong condensate at large scale. So all the dominant interactions has to involve some mode taken from the condensate because it just has too much energy compared to other places. For example, if you want to look at the evolution of the spectrum at this place, at this K, it will involve all the way some modes from the condensate. So in the scale separation limit, that is considered as a non-local. So we are going to assume that only these non-local interactions gives us the signal for the evolution of the wave spectrum. So that allows us to simplify the kinetic equation because we don't need all the interactions. We only need those non-local ones, which will give us a reduced WK wave kinetic equation. And from here, we can explore a small parameter that is Q over K, where Q is a measure of the condensate region that is much smaller than the wave number K, where we are interested in. Okay, so we simply expand this equation using small parameter Q over K. That gives us the spectral diffusion equation eventually. So this is approach one. For approach two, we start from the so-called Zakharov equation. So this is actually similar to the primitive dynamical equation, but with a normal form transformation. So this is not very important, but we start from this equation. Again, we assume the dominance of non-local interactions. That will give us a WKB equation, or sometimes this is called Liouville equation. This equation basically tells us the dynamics of small scales when the large scale structure is slowly varying. Here, the large scale is basically the condensate. And from here, we do some multi-scale analysis. Basically, we are saying the perturbation introduced by large scale is small compared to the linear dynamics of the wave. That could give us also the same spectral diffusion equation. We show through a long process of derivation that these two approaches give us exactly the same final result of this diffusion equation. And then we look for the solution to this diffusion equation that gives us a stationary spectrum K to the -3. So this is an outline. I will tell you a little bit more about approach one, which is probably more straightforward to understand. So for approach one, we start from the wave kinetic equation, which is written again here. And as mentioned, we are going to say that all the interactions have to involve some modes in the condensate region. In fact, there's only one possibility for this to happen, which is that we have two modes in the condensate. Because if we have three modes, then we look at the resonance condition, it will never be satisfied. For the three modes condition, we'll have three modes that are very small and one mode very long, one mode to be very long. So these conditions will never be satisfied. If we only have one mode in the condensate region, there are other problems. The one being that the interaction will be much weaker compared to the situation that we have two modes. So this is the only possibility. And we have two modes, let's say it is K1 and K3 in the condensate region. So this is without loss of generality. And then we can integrate all the delta function in K with respect to K1. So we get the integral containing only K1 and K3. And also this integrand only contains a part of the dominant non-local interactions. And now, as mentioned before, we have a small parameter in Q, which is defined as the difference between K1 and K3 mode. So Q is K1 minus K3. And also here we have K plus Q, that is actually the original K2 variable. So we expand in Q for the integrand. So this is just standard Taylor expansion of some complex function. We'll get order Q term, order Q square term, and higher order terms. When we also expand this in terms of omega, and we write the term in terms of Q into a term that involves the magnitude of K1, K3, and angle of alpha and beta, that is basically the angle between K1, K, and K3. So at this level of expansion, we'll see that omega is symmetric with respect to exchange of K1 and K3. So this basically means if we exchange K1 and K3, this reverses sign, this also reverses sign. So basically omega reverses sign when we exchange K1 and K3, but since omega is in a dot function, so this sign reversal doesn't matter. So on the other hand, one thing to notice is that this whole integral if we exchange K1 to K3, its value doesn't change because this is these are basically dummy variable in terms of integration. So this further tells us that other Q term in the integrand has to vanish, because if it does not vanish, when we exchange K1 to K3, Q is gonna inverse its sign. So it has to be 0 in order for the total value to be not changed. So these are some details. So anyway, after this process, we completely get rid of the other Q term. So the final equation only involves the Q squared term, which is written here. So you see that this equation is already in a diffusion form in the wave number K, because we have a gradient operator here, and we have a divergent operator here. So this is a diffusion equation. Of course, we have a complicated coefficient that involves an integral, but in the form it's a diffusion equation. And from here, we are going to assume that the spectrum is isotropic, so that we only have diffusion in the radial direction, that is in the K direction, not circumferential direction. So if we write this into polar coordinates, and we can ignore the circumferential diffusion because that is isotropic. And we also integrate the frequency dot function that gives us the final result of the diffusion equation only in the K direction. So you see that we have a diffusion coefficient here that involves the integral. So this is a 3-dimensional integral because we get rid of 1 dimension when we integrate out this delta function. So this is integration over d alpha, d beta, and dk1 as an interaction coefficient. And now if we look for the stationary solution for this equation, that requires us to have a good understanding of the interaction coefficient t, depending on k1, k3, in the limit of the small k over k1, k3 over k. So this is a very lengthy computation here, but I ignore the steps because the formula itself is very long. It occupies the whole page probably. But after the calculation at this limit, turns out the result is very simple in the leading order. So it's proportional to k times k1 to the power of 3 over 2. And this is after some significant cancellation of all the larger terms, because in the expression here, it actually involves a term of k squared times k1 that is much larger than this one. But all these terms cancel exactly, so we end up with a simple expression. So we substitute this t into the formula of dk, then we can simplify dk into some constant lambda times k to the power of 4. This lambda basically involves the integral here. All the alpha beta dependents are integrated out, but we still have the an integral with respect to the condensate region. So essentially we have different value of lambda for different condensate, but the k to the power of 4 is the same. So now if you look at the stationary solution, what we do is that we set q equal to a constant. That is the energy flux to be a constant, then we get nk to be a solution that is k to the minus 3. So if you substitute this into the original equation, you can verify that this derivative gives you k to the minus 4, and that cancels with the k to the 4 in the coefficient so that the right-hand side is indeed 0. Okay, so now it seems that we get a solution that is consistent with theory, consistent with simulations and experiments. But there is still a problem. The problem is that this is a diffusion equation, and diffusion only goes to downgrading direction. So that basically means that we have a k to the minus 3 spectrum. The diffusion actually goes to the small scale instead of large scale, but we are expecting an inverse cascade scenario. So what happens for this? So how do we resolve this contradiction? And here is our speculation for this. So basically what happens is this. In the initial stage of pumping energy, we have an inverse cascade which sends energy from the forcing scale to the large scale. And at this stage, there is no condensate forming at large scale because we don't have enough time for the energy to accumulate. So in this stage, we actually have a k to the minus 3 of 23 over 6. And after this stage, after we get enough energy accumulation to form the condensate structure, then the cascade reverses sign to become a forward cascade associated with a k to the minus 3 spectrum. So this is our speculation. Actually, the first picture is already confirmed by some new simulation. I didn't put it here. So they do the inverse cascade, but they measure slope before the condensate forms that agree well with the KZ solution. But the second picture would be the equilibrium of the system, because after sufficient time, everything just stays like this, right? For probably infinite amount of time. So let's do some energy balance for this analysis for this system to try to understand what's happening on this
So-
equilibrium state.
Is the conclusion that are you saying, is the conclusion that the inverse cascade is a transient process
Yeah,
and that the state,
Yeah.
the equilibrium is again?
right. So yes. I think this also happens in 2D turbulence. Because I know in 2D turbulence how people confirm the question and solution that they need to put dissipation at large scale, artificial dissipation, to damp down all the large vortices to see question and solution. But if they don't do that, they allow big vortex to form, then it does not agree with this. So it's a similar. Okay, so what happens for this stage, for the final stage? So first of all, we know that since this is a forward cascade, it will take energy and action from large scale to small scale. That basically means the condensate has to feed the cascade by transferring some action and energy from the condensate scale to the power law scale. And there is another non-local interaction, as we described from the four-wave interactions, that transfers energy from the condensate region to the power law region. So this only transfers energy, but not action, because the action is actually a constant flux situation. It does not need action from otherwhere to sustain the constant. But this is not a constant flux of energy, because when you have a constant action go from low frequency to high frequency, the energy is defined as the action times the frequency. So when you have a constant flux of action, the energy actually becomes larger and larger when you go to higher frequency. And that additional energy has to be provided by the condensate. So you have a non-local transfer of energy in such a way. So both mechanisms will draw energy from the condensate, but we'll need something to sustain it. Otherwise, it will be sucked. All the energy will be sucked from the condensate. That we think that could be some mechanism directly coupling the forcing and the condensate to provide this type of sustaining energy. But this is our speculation, and in order to confirm this, we need to do new simulations to detailed analysis to see whether this is the case. But this is our thinking of what's happening for the equilibrium to establish. How much time do I have? Oh,
It's
maybe I didn't have much time. Maybe I should skip this part. I'll just quickly go to. So this part is basically what happens in the marginal situation in the context of an MMT model. I will skip this part, and there's a paper for this if you want to check. Before ending, I would like to propose something that hopefully some of you get interested, and we can probably work on this together. This is for the forward cascade problem. So for the forward cascade problem, we know that there's a KZ solution. And in addition to that, there is also something called Phillips spectrum that was proposed by O.M. Phillips, who is a famous physical oceanographer and applied mathematician. So this spectrum has a different slope. It is k to the -3 instead of k to the -5 or 2. So when Phillips proposed this, he used a very simple argument. Anyway, you can read the paper, but when I read the paper, I feel that it's hardly for me to believe that it is true. So basically, what he said is that there's a saturation state of the wave spectrum. In this saturation state, the fluid particle of the wave motion had the same acceleration as a gravitational acceleration g, and he said that this is the critical state that wave is about to break, but it does not break. And there is some equilibrium formed by this mechanism. That is what he said. And he said there is only one parameter g involved in this whole process. So that if you do a dimensional analysis, you get this spectrum k to the -3. pretty rough argument. I don't know whether it's true or not, but this is indeed observed in the ocean. And if you see these two figures, it's directly, they are from Dirac ocean field measurements, and you see a k to the minus 2 over 5 over 2, that is the KD solution, but you also see a long range of k to the minus 3. It usually happens at smaller scales. And this is for frequency, the same thing, f to the minus 4 and f to the minus 5. And this solution has never been observed in the primitive dynamical equation simulation. That is probably expected because it will involve some wave breaking process, and that cannot be done in the potential. So I think it would be a good opportunity to do some two-phase flow Navier-Stokes simulation to understand what's happening for the Phillips spectrum. So that is I think a outstanding problem for the field, and we have nothing. We don't know anything about it. It's observed in the ocean, but we don't know what is the mechanism for it to fall. So anyway, I will skip this part, and this work is funded by Simons Foundation. I put the acknowledgement there. So thank you all, and I'm happy to answer questions.
Thank you so much.
Yeah.
For the Phillips spectrum, the experimental data you showed spanned 4 decades. So right. So in the context of simulations,
Yeah.
Can you comment on the scale of the simulations you would need to validate?
Yeah.
this theory?
Yeah, that's a good question. I think it's probably not. If you look at this part, this is almost 50. And then you go to this part, it follows more like so probably say 2 decades.
2 decades.
Yeah, I think we don't need to. Of course, we cannot do DNS for this. It's for the ocean, it's very large scale. So
Right.
we need to make some sacrifice. Probably do a DNS for a smaller scale to see whether it forms, or we do a LES. Probably we don't need 2 decades to exactly match the ocean citation. We just need a range that agrees with Phillips so that we can study the mechanism why it falls.
Yeah, it looks like the Phillips argument, or in the spectrum, is one based on scale separation, where the large scales, maybe there isn't a bound or something. Is that true, or because it just has
I
B
think-
and
Yeah, this is very weird. I mean, the more I think about this, the more weird I feel. I probably not non-local interaction. It has nothing to do with large scale.
Yes.
One thing very weird about this kind of thing that you see that this has nothing to do. The solution has nothing to do with energy flux. But this thing you see there is an energy flux parameter. If you have a higher spectrum, you flux more energy. But this one has nothing to do with energy flux. It's just some weird balance that occurs. I have no idea what to say about its detailed mechanism.
Okay.
Yeah.
The other question I had to do with the, the large scales and the small scales.
Yeah.
I was wondering what it looked like in physical space, and what was
Right.
going through my head was imagining a large scale motion. If I
Yeah.
think of it in physical space, there is local gradients and so on in it.
Yeah.
It can act as production terms. And that's all. If I have length scales that are small relative to a local scale,
Yeah.
that's all they see.
Yeah.
They don't see the long. Is that
Yeah. So
when
in
in
the
your theory, when
Right.
you had that?
in the physical domain, the large wave will be some slow
Yeah.
modulation, and then on top of that, you see some small fluctuation that is small waves. And at this small, I think in the physical domain, the picture is that if you see these small fluctuations traveling along this long wave background, it gets modulated by this long wave to form certain structure. That is what actually the second approach, WKB approach, is
Yeah.
more like this.
Because
Yeah.
wave
Yeah.
equation is slowly varying.
Yeah. Yeah.
I see. So that is the physical
Yeah.
thing that
Right.
very good. Questions for you?
Could you clarify more on the Q parameter where you
Oh.
take the most from the ring and then the Q measures the phase relationship.
By Q, you mean the,
K1 minus K3.
oh, okay, yeah,
Yes.
yeah, okay, so maybe, okay, so here it is what happened. So we have this wave number condition, right?
Right.
So we need K1 minus K3 equal to K2 minus K. This is just written in another way. And we define the difference as Q. So this is both equal to K1 minus K3 and K2 minus K. So when we go from here to here, we integrate out K2 using this delta function. So this vanish and this dK2 vanish. And the remaining thing will have K2 in the integrand. For example, we have K2 here, we have K2 here. So this K2 is basically, from this equation, is just K plus Q. So we convert all the K2 into K plus Q here. So then this integrand only involves K1, K3, K, and Q. So that is how the Q comes into it.
And then Q gives rise to the alpha and beta term. Right?
Oh, this one, okay. So this one, you see that this is a gradient of omega in the K direction. So this term is in the same direction as your K vector. Okay. So you will have a multiplication of K times Q, where Q is K1 minus K3. So you have K vector times K1 vector, and you have K vector times K3 vector. That is why these cosine angle are involved. Yeah.
I have one more. Let me ask one more question. I imagine waves with things like ice or biological material on them.
Yeah.
Can you talk about how how wave turbulence might be affected by those things and
Yeah.
how one might start thinking about those problems?
That's a very good question. This is so in terms of theory, in terms of ice, right? In terms of ice, there are people thinking that when ice is present on the surface, this thing can be considered as an elastic surface to start with. That's a very simple approximation. I believe in that situation, we can develop some wave turbulence theory for that. So what is the spectrum when we have ice on top of wave? If we think of that as an elastic membrane or
You would
something.
homogenize it.
Yeah, that we can do theory.
Hmm.
For if we want to consider more general situation that ice are somewhere with ice, somewhere without ice. At least I know there is no current work in terms of wave turbulence. People probably do simulations, do experiments. Yeah, I don't know how that. Basically, I don't know what is a good mathematical model if the ice are scattered everywhere. So probably there are already something out there, but I don't know. In terms of bio stuff, if let's say we have surfactant on the free surface, that again is a very difficult problem because I think surfactant basically dams the waves. The reason it dams the waves is because it has this Marangoni process, where surface tension is reduced by the surfactant, but so that gives us some stress between different areas of the wave, and that stress is in the it's in the same different direction as the wave motion, so it opposes the wave motion to damp the wave. So it's like we have a very strong damping mechanism that could. So like in turbulence, you have a strong damping, strong dissipation actually that get rid of the inertial range because that strength is much greater than the nonlinear interactions. So in that case, probably we don't have wave turbulence. Yeah, I think this is a case-by-case scenario for different mechanism, for different substance. We have different things to worry about.
Thanks.
But I think it's very interesting to do simulation with surfactant. I'm very interested in that damping mechanism. We did something in the wave tank actually, a few years ago with surfactant, how it damps the wave.
Well, that's
yeah.
Even the ice, so that is bio, it's like could maybe treat it as spatially, even if you homogenize it, it's like a spatially varying property of the background. flow
Right,
in some
right.
sense.
Yeah.
That produces its convolutions.
Yeah.
I got a
Caleb?
clarifying question.
Yeah, sure.
So when you're saying you're injecting forcing, that's like wind blowing over the,
In the ocean, it's wind blowing. In the simulation, we did much simpler than that. We just add a term there, which plays some fluctuation in that scale.
okay.
Yeah,
Okay.
yeah.
Is there a reason that the forcing would occur at small scales more dramatically in the physical situation?
In the physical situation, in the ocean, there is always the inverse cascade because your wind forcing at a particular scale, you will develop both smaller scale structure and larger scale structure. Yeah.
Maybe the forcing question got me thinking in terms of what you said, wind, but maybe something going through it, or can things like schools of fish or something act as forcing to produce waves,
Yeah. It's,
or is that a very dumb question, but it just got.
I don't know, maybe, and it's not a dumb question. It's a very interesting thing to investigate, I think. Yeah, I have no, I have no answer to that. I think it's possible.
or yeah, like a bunch of, like it's raining and then you have a bunch of.
Yeah, it's raining, you will generate these ripples for sure, right? Those are capillary waves
Okay.
with very small wavelets. And but whether that could ultimately have an inverse cascade push energy to long waves, I don't know. If it does, this is an amazing story. You generate wave from rain. That's something very significant.
Okay, very good. Well, thanks a lot, Yulin. That
Yeah,
was
thank you,
really
Mahesh.
informative. Thank
Thank
you
you.
so much.
Thank you, everyone.